This week's lab's on Introduction to Excel. I apologize for my appearance. I've been sick all week and didn't get even a chance to shave, so I'm barely doing this right now. Anyways, the Introduction to Excel is just teaching you how to do the rest of the labs this semester. Largely, we're going to be trying to confirm or, uh, contradict results that we know from laws of physics. So we're looking for some ability to quantitatively figure out how well our theory fits the actual data and evidence. So to do that, what we'll largely do is we'll confine ourselves to variables, one of which will be considered a dependent variable and the other one will be considered an independent variable. We normally put the dependent variable on the vertical axis, that's your y value, for instance, and the independent variable on the x-axis. In a typical experiment, let's say like you were wanting to run an experiment to determine the fuel efficiency of your car as a function of speed, then what you want to do is possibly figure out some way in which you could measure your average speed over the entire trip, or maybe have a constant speed over an entire trip that's long enough for you to measure precisely how much gas you've used and how many miles and how many gallons you've used. So maybe you go on one long trip on an interstate or something like that. Even that, of course, is going to be problematic. But if you can figure out some way to calculate an average, it'd be a little easier. But the main thing is you have some control over that speed. So that speed is, in some sense, oddly enough, going to be called an independent variable because that's not the thing that is affected. That is the thing that's causing the effect. So that variable is going to affect the fuel economy. Therefore, the fuel economy is the dependent variable and it depends on the values of the speed. So you'd put the values of the speed, maybe you did one trip at 50 miles per hour, and you found out what your fuel efficiency was, and you made a plot of that on the fuel efficiency on the vertical axis and the 50 miles per hour on the horizontal axis, and then you did another at 55, then you did another at 60, and then another at 65. Maybe you do some more at 45, 40, 30, 35, that sort of thing. So that's what I mean by independent and dependent variables. But generally speaking, that's the way graphs are supposed to be made: is the dependent variables on the vertical axis and the independent variable is on the x-axis or the horizontal axis, and we call that a y versus x graph. So anytime you hear the phrasing blank versus blank, the first variable is supposed to be the y-axis and therefore the dependent variable. The second word is supposed to be the x-axis and the dependent variable, or excuse me, the independent variable. So in order to do that, we'd like a way to do a line of best fit or even a curve of best fit would be even better because we're not always able to make a graph that is linear. Sometimes it's just not you could probably figure out a way to make every graph linear, but there's a lot of ramifications of that. For instance, sometimes your error becomes exponential. The error in the making of the graph becomes exponential, and that's problematic. So sometimes it's better to just do a plot of the function in exactly the form that it has. Uh, for instance, when Galileo or when Kepler was trying to figure out his relationships between the period of planets and their orbits, he made a plot and he put the period on the vertical axis and the semi-major axis on the horizontal axis. And what we found with all the planets was there was a relationship, but it wasn't linear. So when he did it, he then tried instead of T for the period on the vertical axis and A for the semi-major axis on the horizontal axis, he would then try T and A squared and T and A cubed and T and A to the fourth and stuff like that. And then if that didn't work, he might even try one halves, T on the vertical axis and A to the one half, and T on the vertical axis and A to the one third, and stuff like that. Then he might even tried t squared on the vertical axis and a on the horizontal axis, or t cubed and a, or t to the fourth and a, or t to the one half and a, or t to the one third and a, so on and so forth, and trying all those combinations. And ultimately, what he discovered fit was t squared equals a cubed. So, or t squared is proportional to a cubed. So when he actually plotted t squared versus a cubed, he got a straight line. So that's one of the ways we can take something that's not a linear function necessarily and make it appear linear by graphing the variable raised to some power. That's one of the techniques we'll use, but other techniques we'll use is we'll just graph them outright and say, this is going to be a quadratic function, or this is going to be a third order polynomial, or this is going to be an exponential or a logarithmic, or something along those lines. So my goal here is to show you how to use Excel to do such curve fittings and stuff like that. And I'll even hint to some things that you could do to make your lab analysis even better, so that you can get extra credit points, for instance. So in order to do this, let me start off by I'm not going straight to the document. The document's pretty self-explanatory. You can read over it and follow the instructions. What I'm going to do is go straight into Excel and show you how to use it, and I'm going to use some very specific examples because we've already covered kinematics. I can actually use the kinematic equations and generate actual data that will fit it exactly. I mean, that's not the ideal scenario in terms of a lab, but at least it gives you a comparison. So that's what I'm going to do. So let me start off by sharing my computer screen with you, specifically Microsoft Excel spreadsheet. So here we are, we're looking at the spreadsheet. I've made it 140% of the size that it normally is. Actually, I can make it even bigger. It's not going to matter too much because that part right there is what you sort of need to see, and that won't be very helpful. So what I'm going to do here is I'm going to actually generate data from the exact kinematic equations, and then I'm going to see if Excel is smart enough to do a proper curve fitting, even if we miss the order of magnitude of the polynomial. By doing that, you'll get some confidence in how good Excel and its curve fitting is. So we'll start off. I'm going to write down some initial variables, and those variables are going to be things that I'm going to use over and over again. So what I'm imagining here is a particle that starts at an initial height of y initial, and I'm going to say that is 2.00 meters. If you notice, Excel doesn't consider that 2.00, but it also doesn't think 2.00 is any different than than just plain 2. That, of course, is not the fact. In experimental analysis, 2 flat is very insignificant, whereas 2.0 is a little bit harder to get, and 2.00 is even harder still. So if you wanted to actually make sure you clear that, you could, or make sure you can specify that, then you might want to do something like format cells and then go to number, and then I choose 2 decimal places and I hit OK. So that works. And as always, when you're in the lab environment, it's not appropriate to list any number without units unless it happens to be a pure number. So y initial, which would also be called y0, that's normally what I'd call it. I'm just calling it y initial right now, but I'll put a parenthesis around the meters so you'll know that that's 2 meters. I'm going to say v initial, and again, this is in the y direction. This is going to be in meters per second. And having learned something about projectile motion in general, for instance, I know that basically we're going to lose 9.80 meters per second each second the object's in the air, no matter if I threw it up, threw it down, or threw it horizontally. It's always going to reduce its velocity by 9.80 meters per second each second it's in the air. So to make the numbers work out nice and neat, it might be best if I did an integer multiple of 9.8. So I could take the time to calculate it, but you got Excel. Why would you why would you pull out a calculator? So I'm going to type in equals, and this is the way you get Excel to work as a calculator. Just put equals, okay? So I'm going to say equals, and I'm going to say 3 times 9.80, and that's 29.40. So now what we have is the initial velocities in the positive direction, and I left that on purpose. So we're imagining a ball being thrown up from 2 meters above ground height, which I would say is the origin maybe, and I'm going to throw it straight up, and it's going to go leave my hand at a rate of 29.40 meters per second. The acceleration, on the other hand, which is in the y direction again. So I'm not subscripting these y's because they're all y motion, but the acceleration is acceleration due to gravity, and that's measured in meters per second per second. Again, that's meters per second squared, but if you use the phrase meters per second, it might better help you understand what acceleration means. So in this case, since I said I threw the ball up and it was traveling at 29.40 meters per second and it's a positive, that means the acceleration, which points down, must be a negative. So I'm going to write minus 9.80. So now I have the initial data that I'm looking for. Now, what I would like to do is examine that motion. Specifically, I'd like to find out what the y is at any point in time and what the velocity is at any point in time. I'm going to start with the easiest first, which is the velocity. But in order to do so, I need a time column. So I'm going to write in time, and that's going to be measured in seconds. And I'm going to start off at t equals 0 seconds. Okay. Now I could go ahead and type, zero point 0.5 seconds and then 1 second and then 1.5 seconds. But I'd really like you guys to see how it works even for the first, tenths of a second. So what I'm going to do is I'm going to have it increment the time not by half a second or by a whole second, but by a tenth of a second, at least for the first one whole second. Okay. So one or two, something like that. So I can do that. I can automate that process by typing in the equals and then clicking on the cell above it. So the cell above it is called B6. So I could also just type B6, B6. And what that says is this column is going to be equal to B6. But I don't want it to be equal to B6. I want it to be equal to B6 plus zero point 0.1 second. Okay. If I do that, then I hit here and I get 0.10 second, exactly as I expected. Now I could go back and type that right below this line and do the same thing. Or Excel gives us a better trick. I can grab this little uh, square at the bottom right corner of the cell. I can click on that with my left mouse button and then pull down on it. And as far as I pull down on it, it's going to copy that formula. Now, I really only want it to go about 1 second at tenths of a second, but since I went so far, I'm going to go ahead and go 2 seconds just for the heck of it. So that's point 0.8, point 0.9, 2.0. Okay, so now I've got the first 2 seconds in increments of tenths of a second. And what I want you to see is, remember, I typed in here B6 plus zero point 0.1. When I clicked on that corner and pulled down, it automatically increments any variables the direction you pull it. So for instance, when I pull down, the rows are ordered by numbers and the columns are ordered by letters. Since I pulled down, it's only the column that's the row number that's going to increment. So it went from B6 hopefully to B7 and then hopefully to B8. But let's check and see. And you can see it is B7, B8, B9. So that's what actually happens when you pull it down. Now, there's also a way to stop that, and I'm going to make use of that later. But for right now, I just wanted to let you know that that does happen when you pull down. It's going to increment the row number. If you pull left or right, it's going to increment the column number. So if you pull left, it's going to decrease the column number, the column letter, basically from like B to A or from Q to Oh, I shouldn't have used Q. Go second. P, excuse me. It's the worst letter I could possibly choose. Anyways, so when you pull it left or right, it's going to increment in the direction that you pulled it. And that means by letter. And if you pull it up and down, it's going to increment in the direction you pull it. So if you pull up, it's going to actually increment it by subtracting one. If you pull it down, it's going to increment by increasing it by one or adding one. Now I'm going to go ahead, since I know it's 3 times 9.8, I know it's going to take 3 seconds to get to the top. I know it's going to take another 3 seconds to get to the bottom. And I'm going to imagine I'm throwing this at the edge of a cliff so it can actually go a little bit below it. So I'm going to go further than just plain 6 seconds. I'm going to go maybe a full 8 seconds. But now I only care about it every, half a second. So I'm going to say equals, and I'm going to choose the column above. Now, last time I typed it for you, and you saw how I did that. This this cell above is B26, but I'm just going to click on it. See, it just automatically fills it in, and I'm going to say plus zero point 0.5. And now you can see at 26, I was on a row 26, I was on 2, and I want to go to 8 seconds. So I really need another, for 2 seconds, and I want 8 total. I want 6. 6 times 2 is 12, so I need to go 26 plus 12, it'd be 38 maybe. So let's try pulling this down to 38, and I'm be off plus or minus 1 or something. Let's see. Oops, if I grabbed the wrong cell. Now I'm going to grab this and pull it down to 38. And yes, that does bring me to 8 seconds. So now I've got all the times that I want. Now I would like to know what the velocity is. So we're first doing the velocity as a function of time, and then we're going to do the position as a function of time. So I'm going to say velocity in meters per second. And you know the equation for velocity as a function of time if the acceleration is a constant, and that's v equals v0 plus at. So what I'm going to do is I'm going to type in equals. So I'm literally generating the exact data that our theory tells us, that our hypothesis is that v equals v0 plus at. So I'm going to use exactly that, and then I'm going to do some stuff when I go to curve fit to convince you that Excel didn't just happen to fall upon the right one, but in fact can choose the right one even if you try to trick it. So we're going to start off with V0 plus AT. If you look at it, you'll remember that the initial velocity, of course, is in B2. So I'm going to say uh, B2. So I'll type in a B, but I'm getting ready to pull this down. And when I pull it down, that 2 is going to increment. I don't want that 2 to increment because I want it to come back to this B2 every time. So the way we can stop the variable from incrementing is just put a dollar symbol in front of it. And then I'll type in the 2, and then I say plus uh, V0 plus AT. So the A is going to be B3. So I'm going to type in B. Again, I don't want that to increment, so I'm going to type in a dollar sign. And in principle, you could type a dollar sign in front of B, but it'd be irrelevant because the dollar sign in front of the B would just keep it from changing if I moved it from left to right. I'm not moving it from left to right. I'm going to pull this column straight down. But just to show you that that's the case, I'll put in a dollar sign here, and you'll see that it doesn't matter at all. So I've got V0 plus A. Now I need to multiply that. That's the asterisk, which is shift 8. So now I need to multiply that by the time. Now in the case of the time, I do want it to increment. When I pull it down, the second row should be the velocity at t equal 0.10 second, and the third row should be at t equals 0.2 seconds. So I don't want to put any dollar symbols in that, and that should give me the right answer. And now you see that it does give me the initial velocity, and that makes me feel pretty confident. And after 1 second, you expect that would be 9.8 smaller. If you subtract 9.8 from 29.40, then you'll get 19.6. And we'll check at 1 second, and you should see that that is, in fact, 19.6. Let's double check. So you see it does come down to 19.6 just as expected. That's the very nature of what acceleration means. A constant acceleration of negative 9.8 meters per second every second means the velocity will drop by 9.8 meters per second each second it travels. We did 1 second and it went from 29.4 to 19.6. But I'm going to go ahead and pull this all the way down to the 8 now that we've confirmed that it's acting properly. And now you can see that, in fact, it'll come to the exact same height as we thought. Whoa, Nelly, what's these numbers? Okay, gotcha. Uh, we did think it would reach at 3 seconds. We thought it would reach its max height. At 6 seconds, we'd reach its initial velocity going down, which is what you learned in kinematics, even though you haven't. We weren't. I didn't talk about it a priori. So you see that's negative 29.4 after 6 seconds. That again just reminds us that when you throw an object up, if you ignore air resistance, when it comes back down, it'll be traveling at exactly the same speed, but in the opposite direction. And we see that that's the case. And we still don't know any information about the distance, but we do know how the velocity changes, and it appears that the thing will be moving at 49 meters per second downward after 8 seconds. So it's going to pass, the 2 meter mark, which is the height from which I threw it from the top of a cliff, throw it straight up. It's going to come by me at 6 seconds, where it'll be traveling at negative 29.4 meters per second, and then 2 seconds later it's going to be going 49 meters per second downward. So that is enough for us to actually test the graphing abilities and the curve fitting abilities of Excel. So now what I want to do is show you how to create a graph and then how to do a curve fit. So in order to do a graph, I take and I highlight my X data, which I'm going to treat time as the independent variable, and I'm going to treat velocity as the dependent variable. So I'm going to first take X, and I'm just clicking in the right box, left clicking in the box, and I'm pulling it all the way down to the 8. And now I'm going back up to the Y variable. I click Shift and I hold it down. Actually, I hold down the Shift key and I pull it straight down. Or, but I now have two columns of data highlighted. What I want to go to now is the Insert tab. And over here it says recommended charts. I'm going to do this one right here. It says XY scatter. And in physics and really in the mathematical sciences, when you make graphs, you don't want to connect the dots. You always do a line of best fit. So really all I want right now is the dots, so I'll put that here. But when I do that, I need to make sure that it's actually plotting it in the order that I wanted it. Now, I did select the first one as the X variable and the second one as the Y variable. Even though it acted a little weird, it might just be maybe my latest update just changed the way it behaves. I don't know. But either way, what I did was I highlighted the left column, which is the dependent variable, or excuse me, the independent variable, and then I hit shift and highlighted the right variable. And it seems to have put, since it started off at 29.4, if I click on this point, you see that's 28.42. If I highlight another point, there it is. So you see the X variable is 0.00 and the Y variable is 29.4. So I know it actually plotted the data in the right order like I wanted it to. So what I did was fine. Evidently, it just changed the way it looks. That's why it threw me. But either way, you now see this graph, and it does look like a straight line. That's good because we know the equation is supposed to be V equals V0 plus AT, which looks a lot like Y equals B plus mx. I know we normally say y equals mx plus b, but the way I stated it in kinematics is v equals v0 plus at. V0 is a constant all by itself, so that's got to represent the intercept. And you see clearly the intercept is 29.4. And the slope, the m in front of the x, has to be, since the x was the t variable, it has to be the actual acceleration because v equals v0 plus a times t, where t is the independent variable. So everything did graph like it's supposed to. You can go in and change the title. This is v versus t. And we could go farther and say V in meters per second versus T in seconds, like that. And we could do other stuff. You can label these axes. You can change the gradations, all sorts of good stuff. Uh, for instance, I can left mouse click. I'm not sure if you see the little dialog boxes that pop up when I click on it. But this says format axis. I see delete, reset to match style, font, change chart type, select data, add minor grid lines, format minor major grid lines, format axes, so on and so forth. If I click on the format axes, it gives me choices of the minimum, the maximum, the units, the major, the minor, and stuff like that. So I can actually change the largest number it goes to and the smallest number this line goes to. I can do the same thing with the horizontal axis by, again, in this case, I can right click on it and it gives me again minor grid lines, format major grid lines, format axis, so on and so forth. So those are all things that we can actually do with it after we've made the graph. I know in the PC version, three little windows pop up right here. I'm not seeing those right now, and I usually do see them on here. So I'm really thinking that the update to Microsoft that I recently did, because I keep it on auto update, as you should with a lot of software, just because the software is constantly, the makers of it's constantly finding, various viruses and stuff like that, and hacking tools and stuff like that, and they try to repair them. So if you keep it up to date, you're least likely to get hacked and stuff of that sort. So now that we have this, we can now do a curve fit, and the way to do the curve fit is add chart element. That's what I want. So I'm in a heading called chart design. So I'm in a heading called chart design. So I'll go to add chart element and I go down to trend line. That has an arrow next to it. That's basically like a button that opens up more choices. There I have none, linear, linear forecast, moving average, and more trend line options. I'm going to choose the more trend line options. And it was supposed to give me a dialog box, but it did not for some reason. Okay, it popped up on the other side. Now I've got the more trend line options. So it's suggesting that I want to do linear, so it automatically gave me linear. It was smart enough to know that this is linear. It's got automatic linear series, but I'm going to try to screw it up by saying it's a third order polynomial. So I'm going to click on polynomial of the third order and I'm going to display equation on the chart and display R squared value. The R squared value is a statistical measure of how good the plot is. And if the plot is really, really good, then the R value will be really, really close to 1. If the chart value is perfect, it'll be exactly 1, more or less. Okay, so you always want to include those. And you see that immediately upon me doing that, the equation popped up here. Of course, the equation is in the generic y equals x format, but it is a text box, so you can go ahead and change it to V. Oops, erase the Y first. And then you can say the X I'm going to change to T, and this X I'm going to change to T, and this X I'm going to change to T. And now we have the equation is V equals 7 times 10 to the negative 15th. Remember, 7e negative 15 means 7 times 10 to the negative 15th, which is basically a 0, a decimal point, 14 zeros, and then a 7. These numbers are all on the order of tens or ones. So a number that's, 14 decimals deep is essentially 0. And you see that the second coefficient, the t squared one, is 6 times 10 to the negative 14th. So in that case, it has basically a 0, a decimal, and then 13 zeros, and then a 6. Again, essentially 0. So it really did correctly find us that the right graph was negative 9.8t plus 29.4. So it gave us exactly the acceleration. Remember the equation, if I wrote it in the order that we did, it'd be 29.4 plus negative 9.8t. And the A would be negative 9.8, and the 29.4 would be the V0, and that's exactly what we expect. So it is smart enough to actually do a curve fit even when we give it the wrong type of function. So I gave it a polynomial instead of linear, and a linear is a polynomial, but it's a much simpler version of polynomial. But it did the computation in such a way that it was able to determine that if the t squared and t cubed terms are there, they would have to be so small that they might as well not even count. So that's a really good thing. Now what we're going to do is show you the exact same thing, only this time I'm going to do a position versus time. So I'm going to keep the same time unit, only this time I'm going to say y, and that's going to be y in meters. Okay, our equation for y is the x equals 1 half at squared plus v0t plus x0. It's that equation, of course, but with y. So I'm going to, again, program this data to fit that equation, and then I'll do a curve fit of it. And again, I'm not going to use the exact right curve fit. I'm going to choose one that's maybe a higher order polynomial or something, and you'll see again that it's smart enough to do this. So let's start off with me putting in the y. The y should be 1 half at squared plus v0t plus y0. So I'm going to type in equals 0.5 times a, which remember a is our acceleration, so that's the b3. So I'm going to type in b $3, and the dollar sign, of course, is because I don't want it to increment. And then I need the t, which is the B6, and I want that squared, so I'll hit Shift, which Shift 6, which gives me the caret key, and then 2. Now, when you use that caret key, it basically only squares the thing immediately to its left. If the thing immediately to its left is a right parenthesis, though, then it's going to take everything inside that parenthesis. but that's exactly what I want is I want only the B6 to be squared. So it is doing that correctly. There is also a function in Excel called power or POW or something like that. You can use that too, but I always use this one. So feel free to look it up, and the more you know about Excel, the more powerful you'll be in being able to quickly calculate things. You can even use Excel to solve differential equations very simply if you would like. So it's worthwhile. But anyways, now I have the 1/2 AT squared plus V0. Now our V0 is B2, so I'm going to type in B $2. Again, I could have put a dollar sign in front of the B, but I'm only pulling up and down, so it's not no reason to. So this is V0 times T, and of course our T is B6. And by the way, if I type lowercase b6, it still knows what I'm doing. And then plus y0 in this case, and y0 is b1. So I'm going to say b1. And you see that it does come up exactly with the 2.0. I haven't changed these columns, but I will now to two decimal places format cells. So I'm right mouse clicking on the tops of the columns. I'm choosing number under format cells. I'm choosing two decimal places and I hit OK. And now everything's two decimal places. Now all I have to do is copy this formula down by right clicking, or excuse me, left clicking on the square in the bottom right corner of the box. And I get that. Now that's supposed to be the equation. Ooh, what's this one weird value here? Just double check, make sure my equation looks right. Uh, 1/2 B3, which is blue, and B3 is negative 9.0, so that's good. And the B6 is the time, and that's squared. And then B2 is the initial velocity, and B6 is the time. Oh, and B1 was what I chose. Why did I type B1? It was supposed to be. Oh, wait a second. It was B1. It was B. Yeah. Oh, I know. I forgot to put my dollar sign. I got excited about just typing B1 and didn't put the dollar sign. Oops. That's not good either. So dollar sign one. So there's my boo boo. Everybody see it's now zero point 0.5 times B dollar sign 3, which holds it to B3, times B6 squared, which allows the seconds to increment, and then B dollar sign 2, which holds it to B2, and times B6, which again allows it to be the time, plus B dollar sign 1. Now I've got that correct. Let's check this data again. Luckily, that little value popping up told me that there was an error, so we caught it. Very, very close, but it should be because all I really did was basically start to go down here, and then it added nothing, and then it added the word time, and then it added 0, and then it added point 0.1. So all of that was very, very slightly different from the thing that I had before. That's why it didn't show up. But now I want to graph it again, so I'm going to click here. I'm doing the left mouse button, pull it all the way down to 8 seconds. Now I go over to the third column. I'm going to hit shift. There it goes again. Why is it doing this? I gotta figure out how to do this. Let's see if I'm gonna try one of my other keys. I'm gonna try my option key and my command key. See if I can do it with that. Nope, doesn't do that. Not the command. Let's try option. Option didn't work. Control did not work. Ah, when I held the command key, that's what worked. Okay, so, oh, and I didn't really, I went too far on the first one. So I'm left mouse clicking all the way down to the 8 seconds, and then I push command on my Mac keyboard. And then I scroll down. It's got everything. Now this is what I was trying to do in the first instance, but now we know. So I'm going to go to insert again, plot, but I'm going to choose the scatter plot that's just dots, and you see it gives me that parabola that I want and that I expect. So that looks pretty good. Check in one of the data points as I hover over this. It normally gives me the actual, there it is. So you see this is at 3 seconds. The height is 46.10. And if I look at 3 seconds, the height is 46. So what we see here is this is in fact the Y position, and this is in fact the time from the horizontal axis. So we know it plotted in the right order because literally sometimes when you go to type this or when you go to insert this graph, it'll do them in the exact wrong order. So you always do the horizontal axis data first and then the vertical axis. It's not a big deal if it does it incorrectly. You just have to go through some processes like what those times that I read to you that it said select data. That is one of the boxes where you can go in and change the data the way you want it. It just you have to do a little trial and error. It looks different to me almost every time I see it. So I don't want to just give you away because you see how you have to fumble around a little bit trying to figure it out. But that's basically it. You just have to fumble around till you find it. Or if you did it, every day, or every couple days, then you probably wouldn't forget and you would be able to do it more easily. But now what we have to do is do our graph. So I'm going to still under chart design. I'm going to add chart element, trend line, more trend line options. And I see that when I did that earlier, it did actually work. It's just I didn't notice this box had popped up because I think it might have been another box before there, but who knows? Uh, uh, anyway, so this time I'm going to do another polynomial. We know it's a second order polynomial, but I'm going to go ahead and punch it up to the fourth just to see. And I do want it to display equation on the chart and display r squared. By the way, when you're doing linear expressions, like for instance Kepler's data, you do expect a period of 0 years for a semi-major axis of 0 astronomical units. So you might want to just force that by saying set the intercept to 0. That's what that's for. So you can do that. I occasionally, like when we're doing something that's supposed to have no intercept, sometimes you might get a slightly better graph by setting the intercept to 0. But what should lead you to conclude that it's a slightly better graph is not that you got less error compared to the accepted value, but the fact that you got a better R value. The R value is sort of the statistical tool that tells you, hey, this is how good this graph is. And then if you set the intercept to 0 or to whatever you choose to set it to, and the R value gets better, then you have a substantive reason to set the R value to 0 as opposed to just fudging. Okay. In this case, we can see it did actually uh, graph a fourth order polynomial, or it gave us a fourth order polynomial. It is y, but it's y versus t. So I'm going to go ahead and erase the x's and put t's in there. But you'll notice we knew it was a second order polynomial because that's what we put it in there. But we actually ordered it to do a fourth order polynomial. And you see that the coefficient of the fourth uh, power is 7 times 10 to the negative fifth, which is 0 point followed by 14 zeros and a 7. And the third order coefficient is 3, or excuse me, is 0 decimal point, 12 zeros followed by a 3. Again, essentially 0 for those first two terms. So it was smart enough. And in fact, it did get exactly negative 1/2 a for the coefficient of t squared because a is 9.8 and half of that is 4.90. A is technically negative 9.8 and half of that is negative 4.9. So it did get that. The initial velocity was 29.4 and it got exactly that, and the initial position was 2.00 and it did get that, and you got an r squared equal to 1. That means the graph is really great, and that's what we expect. Now, as far as what the software is doing here, it's doing something that you learn about a little bit in calculus, depending on how intensive your calculus course was. You learned about Newton's method, which is one way to approximate zeros of a function and stuff like that. In this case, what they're doing is, and different software packages can implement it different ways, but you could take, for instance, the distance, vertical distance between a single point of data and a point on the actual graph that you've hypothesized is the right graph, and you measure that, and you do that for each of the data points. Some will be positive, some will be negative, and then you, instead of taking just that value, you square it because otherwise you'll get positives and negatives canceling each other out. But what you want is not necessarily them covering each other out. You want their distances to be a minimum. So you take and create sort of in some idea a function that represents the sum of all those distances between the vertical distance between each data point and a dot on the chosen hypothesized graph, and you're squaring all those and add them all together, and then you're taking the value of the graph that actually gives you the smallest number of those sums. And by doing that, it gives you what we call a least squares fit. So you're calculating basically a least squares fit. So it's unambiguously and unbiasedly calculating the best fit of the data that it possibly can. That's something that, Newton and Kepler didn't have access to in any way. They could have, even if Newton had come up with it, which he came up with Newton's method of finding zeros, so he probably could have come up with this. He probably couldn't do it in a reasonable way because it would take, millions of calculations. That's a pain, but computers are really good at that sort of stuff, and you can see it does it the instant you hit the button. So that's the big goal for this lab is you guys to learn how to apply Excel to various graphs. I've shown you everything you need to know in terms of how to add them. I've shown you how to add the title, how to change the title, how to uh, change the way the graph axes are labeled, and I've shown you how to do curve fits. I haven't shown you something else though. There is, for each of these curve fits, there's a way, and Excel will tell you if you want to look into this, there's a way you can find out not just R squared, but you can find out the error in each of the variables. Because if you have an equation like y equals mx plus b, and Excel does a curve fit for it, then the R squared is sort of one value of the error of the graph and how it compares to the actual data. But you might want to know, well, how does the actual coefficients, the m and the b, for instance, how are they? How precisely do we know them based on this curve fit? In order to know that, you need to know the error of those variables. And in fact, Excel has a way where you can say, okay, Excel, now tell me what the error in this 7.5 or 7 times 10 to the negative 15th number is. Tell me what the error in this 3 times 10 to the negative 13th number is. Tell me what the error in negative 4.9 is. Tell me what the error in 29.4 is. And tell me what the error in 2.0 is. Now, that's really what you need. For instance, if you were to analyze this, get these numbers, the negative 4.9, the 29.4, and you had to use them in some subsequent calculation, then you need to allow the error to propagate. What you've determined, if you were instead of trying to confirm a theory, you're instead trying to generate a theory where you're just taking data and you don't know what the results are supposed to be. You're looking at it and it looks like a second order polynomial, so you do a curve fit and then you say, okay, well, how am I going to use this data going forward and take into account its error? Well, any calculations you do with that data would have to have the error of the curve fit propagated as well. So you couldn't do that unless you knew the error of the individual coefficients. Excel does give you ability to do that. So that's a sort of challenge for you guys. If anybody can find out some stuff about that and write it up in the lab when you turn it in, then I'll probably give you at least plus 5 points for telling it. And for instance, with any particular graph, maybe you could do these same ones I did, or maybe you just take one of the ones that you do in the lab manual. But if you give me that information, show me exactly how what the errors are of the coefficients you solve for, I'd be very appreciative. And like I said, I'll give you plus 5 points on the lab report grade. Uh, that doesn't mean you automatically get a 105. You still can get points off for other things, but it means you're going to get 5 points higher. So other than that, the labs are pretty much just the way they always are. You're going to take the lab document, the Word document that I gave you, and you're going to type in anywhere you see a question. You're going to put a cursor to the right of the question mark and you hit return, return, return. And then in the middle of the white space, you're going to enter using a text or drawings that are a font or a color other than black. And you're going to answer the question and you're going to answer all questions. And even if it's, well, sometimes they'll say show the graph or plot the graph or show the data or something like that. I want to see all the graphs, and I'm never going to take off for you giving me more graphs than necessary. I just want them put in the proper place. So err on the side of giving me a graph, even if it doesn't explicitly say you had to give it. But if you tried, multiple different types of curves to fit one thing, I'd like to see exactly what graphs made you throw that data out. So for instance, if you graph something as, a third order polynomial, but you found out a fourth order polynomial would be better, I would like to see the third order polynomial graph so I can figure out why you think that a third order wasn't sufficient. So even though it doesn't tell you to explicitly do that, uh, we mostly wrote that lab manual so you wouldn't have to print so much and use so much paper. But in this case, the way we turn in our labs are all electronic, so it doesn't bother me to have extra graphs because we're not actually printing any paper. So hopefully that helps you. Let me go ahead and kill this now. So I'm going to do file. Actually, I'm just going to exit this screen. Now I'm going to share my other computer screen, which I believe is right here. So this is our Zoom meeting, but what I want here is not that, not that. Right here, I'll pull this open. I want to show you the actual lab document now. Again, that's not the most critical thing. It's just like we do every week. But here it is down here, week 4 lab module. Here's a video where I've introduced it in the past. You're welcome to watch that. You don't need to, but you're welcome to. This is the Word document that we're using. And you can see it just tells you what to do. Like here's a question. Okay, this one you were fortunate enough to have them give you a blank, but you have to answer that question, and it should be in a font other than black. Pay attention to all the questions. Answer all the questions. There's a question. This is one that a lot of students forget to answer a lot of times, and they lose points in increments of 5 every time they do it. This explains more or less all the stuff I just did. This is some more stuff. Here's another question you're supposed to answer. But you can see this is basically the document that you're going to be filling in. See, add trend line, more trending options. Same stuff I explained. Uh, this latest update might be slightly different. I know mine's showing some windows that I'm not used to. It caught me off guard. I apologize for that. But anyways, it also tells you how to select the data. I had to use the command button on my Mac, but I'm not certain exactly which one you'll use on on the Windows operating system. But trial and error will get you there. I'm just not in there right now, and I don't have a PC personally. I just have the ones I use at work. Here's some more stuff to answer, more stuff to answer. Another graph, more stuff to answer, so on and so forth. So that's the actual lab report, and there's no addendum or anything needed for this one because this one can be done online or face to face with no problems. So that's why there's not an addendum. I'm going to go ahead and go back to the modules now. I thought I was. Now I'm going, maybe. All right, go down to week 4 module. Notice I also did make practice test twos available. That is on I think it's the 15th is what the 2/15 is when the second online test is due. So I wanted to make sure y'all had plenty of time to do that. So I went ahead and made it available. I did it this morning. That's why I'm reminding you now, uh, because I'm liable to forget by the next time I talk to you. And this is where you turn it in. That's the main thing. It's due the 12th, which is a week from today at 11:59 p.m. Contact me if you need any problems. Remember the way I grade my lab reports. If you have generally speaking, even though I'm not tied into this, if you have the lab report in before I grade it, I'm almost certainly not going to take points off. But don't rely on that because sometimes I grade it right at the time it's supposed to be due. So like sometimes I'll grade it the same night it's due. I usually don't get to it that quick, but sometimes I do. So try not to do that, but just know that if you ever, screw up one day, it's probably not going to be a big deal. It'd probably be fine if you turn it in the second day. So with that, since there's no one here, I'm going to go ahead and call it a day. And thank you all for watching, and I hope this is clear. Feel free to text me. I did get a couple of texts last night, actually last night and yesterday, but I've been sick, so I haven't been paying much attention to anything. I apologize. I haven't replied. I know I should within 24 or 48 hours, but I don't do that when I'm that sick. So I apologize. But have a good weekend, folks, and I will see you next time. Bye bye.